Particles or waves? The quantum mystery. Quantum mechanics reveals a mind-bending truth about our world. It takes us back to an age-old debate. Is nature built from tiny particles? Or from flowing waves? Or could it be both? Alright, let's rewind the clock a bit. Back in the day, the legendary Isaac Newton was firmly on Team Particle. He made some awesome discoveries, like figuring out that white light is actually a mix of all sorts of colors. And get this, you can even put those colors back together to get white light again. Pretty cool, huh? Newton thought about light like it was made of tiny little particles. Kinda like grains of sand. He even wrote a whole book about it called Optics. This particle idea helped him explain how light bounces off things. That's reflection. And how it bends when it goes from air into water. Or through a lens. That's refraction. But here's where it gets a little tricky. Newton also discovered something called Newton's rings. These are these crazy colorful patterns you can get when you press a curved piece of glass against a flat one. Turns out, these rings are actually a sign of light acting like a wave. Which kinda threw a wrench in Newton's particle theory. So even the big guys like Newton didn't have it all figured out. While Newton was busy with his particles, there was another brilliant mind on the scene. Christiaan Huygens. And guess what? He was team wave all the way. Huygens had his own ideas about light, and he wrote them all down in his book called Traité de la Lumière. He imagined light spreading out like waves on a pond, which we now call the Huygens-Fresnel principle. This wave model helped him explain some really cool stuff, like polarization. You know, how some sunglasses can block out glare. That's polarization in action. Huygens also figured out that sound travels as a wave too. And remember those pesky interference patterns that Newton struggled with? Well, Huygens' wave model explained them like a charm. So, you see, back then, there were two competing ideas about light, particles versus waves, and both sides had some pretty strong evidence to back them up. It was a real scientific showdown. Fast forward a bit, and along comes James Clerk Maxwell. He cracked the code on electromagnetism, showing that light is actually a wave traveling through an electromagnetic field. This was a big win for Team Wave. By the 19th century, most scientists were convinced light is a wave. Case closed. But then, around 1900, Max Planck dropped a bombshell. He proposed that light isn't just a continuous wave, but it's also absorbed and emitted in little bursts of energy. He called these bursts quanta. And a few years later, Einstein used this idea to explain something called the photoelectric effect. The photoelectric effect is like this. You shine light on certain metals, and it can actually knock electrons loose, creating an electric current. But here's the weird thing. It doesn't matter how bright the light is. Only light with a high enough frequency, that means a specific color, can do the trick. Think of it like trying to kick a ball over a hill. If you don't kick it hard enough, it'll just roll back down. No matter how many times you try, you need one good, strong kick to get it over the top. Same with the photoelectric effect. You need light with enough energy per photon to knock those electrons loose. So, Planck and Einstein's work brought back the particle idea in a big way. It was like the particle versus wave debate had been reopened. And guess what? It gets even crazier from here. Alright, now it's time for the grand finale. The double-slit experiment. This is where the wave and particle sides of light really come together to blow our minds. Picture this. We've got a light source shining one color in all directions. It hits a wall with two tiny slits in it. Behind that wall, there's a screen that captures the light, kind of like an old-school photographic plate. First, we close one of the slits. Light goes through the other slit, and we see a single blob of light on the screen. No surprises there. We switch slits. Same thing happens. Just a blob in a different spot. But now, the big moment. We open both slits. What do you think will happen? Two blobs? Nope. We get something way cooler. An interference pattern. It's like a series of bright and dark stripes on the screen. His pattern is a classic sign of waves interfering with each other. It's like ripples in a pond crossing paths and creating those peaks and troughs. So, case closed. Light is a wave, right? Not so fast. Now, imagine we dim the light way down. Until it's almost pitch black. We start seeing something different. The light hits the screen in individual spots. One at a time. Like tiny little bullets. Remember the photoelectric effect? That told us light comes in these little packets of energy called photons. And here they are, showing up as individual spots on the screen. So light acts like a wave when it goes through the slits, creating that interference pattern. But it also acts like a particle when it hits the screen, showing up as those individual spots. It's both. And guess what? It gets even crazier. We can do this experiment with electrons instead of light. And we get the same result. Even tiny particles like electrons have this wave-particle duality. It's like each electron goes through both slits at the same time, interfering with itself. So, how is this even possible? How can something be both a wave and a particle? The answer lies in something called the probability amplitude, which is based on the idea that the entire world is fundamentally made of waves. And that, my friends, is where we dive headfirst into the mind-bending world of quantum mechanics.